get to the subject today, I asked someone to confirm that you can hear me. It's very quiet. Okay, I will just check if some setting. Okay, maybe now it's better, I hope. Yeah. Okay. I'm not sure why the new version of the Zoom always makes the microphone almost muted when starting a new lecture. Okay, let's begin then. Subject for today is kinematic structures. I hope it will be a little bit more, one of the easier subjects to deal with, because I would like to tell you about some different types of the manipulators that we can meet. You have probably already seen, so it is like more like putting some knowledge together in order, and maybe showing some aspects that may be not quite obvious, and but it's worth to know about that. Okay, so what we are going to talk today are the structures that are non-serial. I think you already seen. Okay, we are talking about manipulators, so not the mobile robots this time. And what you usually already know are the so-called serial structures. So we have links that start from the base, and one link is connected to another, to the next one, and they just form a ordered serial line. At the end, we have the effector. But apart of that, we have other types of structures that are non-serial. So there we will have joints that are connected in more than one point to another joints or to the ground. And what we will see here. Firstly, there will be the tree structures. So the tree structures are the elements that start to branch at certain place. So first example, articulated hands. So we have, let's say, this palm of the hand, and from that we have the fingers that are connected to the others. So it is like a manipulator with multiple branches. Yes, it can be even somewhere on the hand. We have the joints in that places, but we cannot describe it in a. Okay, the kinematics is more complex to what we were presenting in the previous semester, in that sense that we don't have only one line of the kinematics as we had in the standard manipulators, that we were just going from this point, like it was like, okay, let's change the color. We are going like this, connections and so on, and we are just multiplying these matrices. It will partially work like that, but in fact we can treat each of the tips of the fingers as separate effectors. So in fact we will have one kinematic solution for this, another one for this chain, and this chain, and this chain. So in fact we have like 4 effectors and 4 different kinematic chains that we can consider. Okay, so articulated hands. Then the leg robots. When we have a leg robot, okay, this one will be mobile. We can say that, okay, that's one link, another. We have one link, another. That's the standard 6-leg robot. When you place the base, okay, the center of the robot in the middle of the support, you can treat this as a one kinematic change. Each of the legs has separate kinematic change. Again, a tree structure similar to hands, but differently than in hand. The hand has a base somewhere here, the starting point. This one has a base in that point on the center of the body. What else we can have? We can have also walking. Okay, other robots like walking robots, and also this type of multi-leg robots can also be treated as closed chain robots. What are the closed chain robots? Closed chains are the kinematic chains that are connected more than one time to the ground. So when we have the ground and we have a, let's say, humanoid walking robot, that's we have the torso, we have the legs, and the legs are attached to the ground in more than one point. Of course, during walking, they can change to the tree structure when they raise a leg, and then they can be again the closed chain when they touch the ground with two legs again. Other chain robots will be like multi-bar systems. So we will have like elements that are just connected in more than one place, and they will be attached to the ground in more than one point. We will see what are the consequences for the solutions that we have, especially in they will appear special. You will need to treat especially the closed chain robots because, okay, you can try to solve them as the kinematic, using the standard kinematic approach, for example, like here, but the endpoint is not a free one. You cannot change it. So it is like a kinematic with the constraint that is fixed. So the end effector, if you treat it as a standard serial robot, starting, let's say, from here until the effector here, the effector is attached to the place and it's fixed in that point, and you have like a two boundary constraint on each end to be solved. That makes some complications that maybe you know from other fields. That is, the two-point boundary problems are not so easy to solve. Okay, so let's go into details, and we can see why the robotic hands are in the interest. There are different approaches how to solve it. Generally, the robotic hands are being developed because of the two reasons. Firstly, because our world is prepared for people. If we want the robots to naturally fit into the environment in where people appear, for example, we want a domestic robot that will do some that will help people with some standard home tasks. You may probably want the robot to be able to use the same tools and the same equipment. It means that it should have similar reach and similar manipulation abilities as the human does. So you don't need to exchange the devices that are at home for the special devices suited for the robot. Another direction and another reason for developing the hands are the purpose of working with people with disabilities or enhancing human capabilities. So it means either the prosthetics or the exoskeletons. So they imitate the movement of the hand, either to replace the human hand or to equip it with the additional, usually the force ability. Okay, when developing the hands, people usually need to consider multiple types of the grasp. If you start to think about it, look at this image, you can see that the human hand is quite a versatile device, is able to do multiple different functions, multiple different types of the grasp that can be used. So and that's why it is quite a challenging problem for the robotics. And when we look of what are the current development of the anthropomorphic hands that are available on the market or developed, or they are just research projects, you can see some examples. Those that are mentioned here are quite either mentioned because they are important in the as a major steps, or they are just currently available like this. The last three elements, that ultralight, shadow, and DLR, which are, let's say, the top solutions in certain in certain aspects. So as you can see, what we try to imitate is this one. So the human size hand has 5 fingers and 22 degrees of freedom. Yes. So as you can recall, these manipulators that we work like FANUC, or most of the industrial manipulators have like 5, 6, 7 degrees of freedom, a single hand, and it's counting from the palm. In fact, it is 22 degrees of freedom. And you need, if you want to really imitate it, let's say for the purposes of prosthetics, you need to not only imitate the capabilities of the movement, but also the size and and have a reasonable weight of it. And you can see what are the solutions. So the first approach from 79, so it's like almost 50 years ago, were just 3 fingers and 11 degrees of freedom, and it was was bigger than the real human hand. Was using the tendons and electrical actuators. You can see also in these tables also the drives that were used. So what were the actuators? Were there motors or pneumatic actuators or other types, and the types of the transmission from the actuators to the joints. And you can see that the number of degrees of freedom grows, the number of fingers grows. Also, the solutions are usually more bigger than the real human hand, although we are trying to get to the size of the human hand in the latest solution. In fact, when you look at this DLR is the German Space Agency. The robotic hand is just a part of their project of making an artificial human-like robot, which they want to use as a, let's say, a robotic astronaut. that can be sent to the space station instead of human astronauts. Okay, so you can see it's kind of difficult. It is already shown that, okay, the minimum amount of fingers that is needed to be able to manipulate with objects during grasping. So when you already keep the object and you, for example, want to rotate it or want to do something to it, you need at least 3 fingers, 2 to keep the object and 1 to perform the manipulation, switching between the fingers. But of course, with more fingers, you can do it more, manipulate with the objects more easily. But as you probably know, when you have more degrees of freedom, it usually means that you need, if you want to have these degrees of freedom to be fully independent, each of them must be associated with own actuator and the own transmission, because you usually cannot place the actuators in the joints, so close to the joints, especially in the fingers, if you want to keep their size. So you need to place the actuators in the arm before, and somehow to transmit the power and the movement to the joints itself. And that's the additional elements that you need to care of. Just to see some examples of how they work, we can observe 2 of this. One the so-called super hand. And as you can see here, you have the tendons that just transmit the actuators movement. The actuators are hidden here in this forearm. Using the tendons has certain properties. Firstly, they can you can transmit it to the longer distance, but because they when you apply a force, okay, that's something that is not a nice treatment of the hands. But what we have with the tendons is that when you apply the force, the length of the tendons can change. So you have some uncontrolled movement that may appear. On the other hand, they can be reliable and robust to the impact forces, as you could see on the video. Another approach you can see using instead of using as a prosthesis, you can use as an exoskeleton. When you have your real hand, you don't replace the hand, you just extend the capabilities of the human hand with the robot. In fact, when you look at it, you may notice that a part of the finger grips, you have some mechanisms that are outside of the hand, above the hand, and those are some parallel mechanisms, and we will be talking about it in the second part of today's lecture. So please just notice that although they were separated, the tree structures and the closed loop structures were separated. In fact, you can also have the solutions that combine two of them. Okay, so if someone wants to see, those are just the videos that are available on YouTube. So just look for the Festo exohand and you will be able to see what are the capabilities. Okay, so those are the examples of to the left, the shadow robotics and DLR, just the top solutions that we have industrially available. But you can also find other options. For example, TICGen has a proposition of the solutions with completely elastic fingers. We are talking about the elasticity already of how it influences the capabilities of the movement. So it can be also used. It is more difficult to control, but also it requires less actuators. In fact, here you have only one actuator per finger, and you are able to deal with quite a high amount of movement. So the two directions, complicated, complex, and expensive solution from Shadow or DLR, and quite simple. As you can see, it's mostly 3D printed, a solution that is cheap, but also has, because of the low price, has also some advantages. Okay, maybe we will skip the part of the model, of the exact model, and let's talk about the hand kinematics, and let's look at the example of it on this drawing. As you can see here, you have the palm, you have the fingers that are attached, and when you represent it as the using the standard, let's say, mechanical representations, you can see how the joints are placed. Yes. So if we treat this point O as a center, you have the thumb that has like one rotation. It's this rotation around this axis. Then you have this rotation, and so on. As you have this representation, 4 degrees of freedom for the thumb, and again you have one rotation, second, third, and fourth. So again, four rotational joints for the fingers. You can see here is like this rotation, and this, and not the visible next one. Okay, and then when you get the task to solve the kinematics of such a structure, you may start to think of, okay, so what are the interest points and what are what we want to control? And when you start to think about it, you can realize that, okay, you may consider the end of the tip of the finger as an effector point, and that will be this point. But also, when you try to close and grasp some objects, you may touch it also with another, like let's say the phalanx, so another part of the finger. So you should also be aware of what are the other points. So we can say, okay, we are not only to draw. So we are not only interested with what this point attaches, but also if this point does not collide with an object. And similarly with these fingers, you will have more points to control. And all these points you have marked with the S with index. First index is the number of the finger, starting from 0 as thumb, and the second one is the number of joints starting from the palm. So that's what you will see. And as you can already imagine, okay, we will get a kind of the structure that says, okay, if you want to solve, let's say, SO2 kinematics, we need to start from the base, go first joint, second joint, and the third one. If we go to the SO3, we have the same first 3 joints and 1 additional joint. So the first kinematics of each finger is not independent. Just the next point depends on the previous one and maybe some additional rotation. Then you will have that many chains of kinematics. How many points of interest you have found. So depending on task, you can say, okay, either only tips of the fingers, then we will make it simple. We will make like three separate single manipulators, or we can just consider all these points, and then we will have a real tree structure. Okay, so what we do with the calculations? Of course, you can take some parameters. Okay, they are not really important in that case, but you can use again the Navitt-Hartenberg's representations for all of the parts, and then you get the formulas for the calculations. And in fact, that's something that is important to look at it, because we can. When we look at it, you will see that we can split it into 3 parts. The first part is in fact constant, and the third one is also constant. And let's assume that we are describing this point. So what will be the first part describes the connection between, let's say, the base and the place where is the first rotation. If you just treat this finger as a separate manipulator, you could say that, okay, this finger is attached in this point, and this is our base because we are rotating in this point here. But in fact, if we want to control all fingers in a common coordinate system, we need a common coordinate system position. So this part will be our first transformation. Then we will have a second part of the transformation, which is a transformation until the beginning of the last joint. That's the second, and this one is dependent on joints. And the third one is again a fixed part, constant, that says of how our point of interest is located with respect to the beginning of the link. Why we split it in that way? Because, of course, we can have another joint and another interest point on the next link, and we need both the transformation to our point of interest. We want also a transformation to the next joint for the purpose of the further kinematics. So that's what we get. We have just these 3 components, and the middle one is just a transformation of the is just a transformation that we know already from the kinematics. All of these are just the multiplication of the matrices. in this exactly the same way as we were calculating during the course on last year, but the only difference is that you need to say, okay, we just explicitly calculated with the Nabit-Hartenberg the second part, but we also need to add a constant matrix before and after to make a complete solution. And that's in fact is a difference. Not too much in the not much more difficult in calculations, but just you need to remember of what's going on. And another part that instead of one formula, you will have that many formulas, how many points of interest on the hand you have for your current grasp. And how many of these points are, it depends on what the grasp you have, because, okay, let's say that you have, if you want to grasp this small ball, you will use something what is called tip or pinch grasp, and in fact, you need for that just 2 points where you touch. When you try to catch a bigger object, you may need, like here, like 4 points. In fact, it may be even more. In the cylindrical grasp, like here, in fact, you can use not only these 4 points, but probably some support. So it can be 7 more, depending on what exactly this grasp was. And things may get even more complex when you get to grasping such an object as a jack. And so you can have not when you need support in different directions of the object, that you not only need to consider kinematics, but also the force distribution of the object. So when you look at it, okay, it becomes a bit more difficult. Then you can apply the formulas that we are talking about when we are saying about the grasping of what's going on. Just remembering that we need to use higher number of contact points, higher number of these touch points that to be considered, and that because of the higher number of the degrees of freedom, we have more influence of what will be going on, more capabilities for the robot to do, but of course the solving that will be more complex as well. Okay, so let's get then to the second part of the objects, that will be the closed loop structures. And as a starting point, I was marked the 5-bar system, but in fact, before we start with 5-bar system, we will talk about the so-called 4-bar system, and maybe just to give some intuition and get some feedback from you of what do you think. Okay, so let's imagine that we have an object like here. We have a joints, rotational joints in here, and we have one link in this place. We have the second link, and these links are rotating. And then we apply also using one more bar, and we also connect it with an option of rotation. Okay, and now a question for you. We have, let's mark it in a different color. We have 1, 2, 3, 4. 4 joints. Okay, the color is maybe not the best for writing anything. 4 rotational joints. Now the question is, how many degrees of freedom we have in these objects? How many independent controls we can apply in these joints? Anyone tries to guess or knows the answer? So our question: how many degrees of freedom? Let's have 30 seconds to think about it. Either someone say it or put it in chat. Okay, so let's start with a simpler case that you already know. Okay, so let's make it just a serial manipulator. One joint, second joint, third joint, and let's say that's the end effector. Okay, we have the same number of joints. How many different controls we can apply? Independent controls. Can we move separately and rotate separately each joint? Yes or no? So yeah, here we have 4 independent controls. So in fact, there is 4 degrees of freedom at the level of the joint space. Yes, because that's something that we are talking about. Okay, so let's return, and that's typical for the serial manipulators. When we have 4 joints, okay, we say about the so-called 5-class joints, so the joint that can rotate only in one axis. They are of the other class joints that can have additional movement, but okay, let's assume that those are standard one axis rotation. So the number of joints is equal to the number of the degrees of freedom in the joint space. But what happens when we attach one end? Yes, we attach the second and let's say the end effector. If we just take this one, grasp the objects at the ground, and we get fixed to that point. what happens? Okay, so let's look at this object and say, can we move it at all? Is it zero or not? Okay, because now if we know the limit, that the limit is 4, so we need to decide somewhere between this, yes? So can it be 0? So because it may happen then that the objects cannot move at all under some conditions. We will present such examples later on. So is it 0 or not? Okay, just to make it active, on the participant list, you have an options to say yes or to choose the yes or no. So who will say that we have 0, give yes, and we say that we don't have 0 and something more, say no, mark no. And we will see how many of you is actively listening to what's going on. Yes, so we have 1 no and 13 of no opinion. Okay, so we excluded 0. So let's imagine then that we are starting to rotate one joint. Yes, so we know that we start to rotate one joint freely. Okay, what does it mean? We rotate it to a certain degree. It means that we already set this point, yes? Because if we say we rotate by 30 degrees, we know where this point is. And we know that we have 2 known lengths of the manipulator, and we know that this point is also attached. Now the question is, can we move this point somewhere away or not? And again, you can raise your hand and say, is it possible if we have the fixed length of these 2 arms, we know by moving the first joint to a certain position, we know where this point is. So do we get another option of movement or not? Can we move it? Can we move this point here? No. One answer of no. And yeah, and that's the correct answer, which says that we don't have this one. We have only 1 degree of freedom. So despite of having 4 rotational joints, we can use only 1 actuator to drive this, because all the other position of the joints are dependent on the first one. So we have only 1 independent rotation. It doesn't need to be the first one. It can be the last one. It can be any of them in the middle. Of course, practically, it will be some joint at the base, but it doesn't matter if left or right. But we cannot freely move the other ones. Yes, of course, it's a good assumption that they are stiff. Yes, we are saying about the stiff elements. We don't try to bend it. What will happen if we attach 2 different actuators and we try to control them independently? Then we will get some troubles, because they can apply the force against each other, and that may, okay, at least we will be losing some energy, but we also will be attempting to destroy the mechanism, either the actuators or the mechanism itself. So generally, we have one degree of freedom with 4 joints. So all the other 3 joints need to be free rotations that will be just passively react to this first actuator. Okay, but this one is called the, what was drawn here was called the 4-bar. So this one was the 4-bar. So maybe the question was why we have 3 bars and where is the 4th one? So this part is the fourth part of the construction. Yes, this base is the in the naming, which is taken from the mechanical theory. They don't say about special treatment of the base. It's just a fourth element of the mechanism. Okay, so let's get to the 5-bar system, and 5-bar system will look like that. Okay, so we have again 2 attachments, and we have, okay, let's say 1 part here, we have the second here, third, and the fourth one. And if we mark the rotations, we have 1, second, third, 4, and 5. So we have these 5 joints in our system, 5 rotations. And now the question is, how many degrees of freedom we have? But maybe also what is the workspace of this robot? So let's start with the degrees of freedom. Will it be 1 as in the previous case or more? Yeah, one answer that says 2. Someone else? Are there any other opinions? Who will agree that those are 2? Yeah, so it is more than 1. Again, we can think about it as in previous case. So okay, we rotate it to the certain location. So we already know where this point is. We rotate, let's say that what happens? We have then, maybe instead of using this part, we will use the already present. So let's say we fix it in that place. Can we move with these points independently? Yes, it seems that we can. So it is more than 1 for sure. So now let's start to rotate. Let's say that we fix the second one, and so this point will be fixed. So we rotated it to the certain position, and now we say, okay, that's the setting of the second joint. Can we move that point then? And it appears that we cannot. So yeah, we get 2 degrees of freedom then. Okay, 5 joints, 2 degrees of freedom. What can be, how to approach determining the workspace of this manipulator? How it will look like? How do you think? Maybe someone has an idea of how to develop this what is the procedure of finding out this this workspace. Okay, one of the something that we already did again a year ago, as everything is connected somehow. Okay, imagine that we just take a half of it. So we just split it in this point, disconnect this joint for a while. What happens? Then we will have like two double pendulums. And as you already know and remember, okay, I will make the drawing a little smaller so it's easier to draw for me. As you know, the double pendulum has a workspace more or less like that. So it is like a circle of the length of L1 plus L2 with exclusion of the smaller circle resulting from the difference between the lengths. Okay, so this is our workspace. And when we look from the second side, you can say, okay, it's again a circle with excluded middle circle. So what will be the final workspace of this manipulator? Is the place where two of these pendulums reach at the same time. Of course, depending on how big the base is, they can be bigger. They can even start to cross in that part, and then the shape will be more complicated. But that's more or less how you get it. You combine these two shapes of separate double pendulums workspace, and you find the common part of it, and that's the workspace of this structure. Okay, that the structure is not really virtual and just artificial academic. It's just where these robots can be used. And it is just an example of how it is done. Okay, the structure is here a bit. Okay, and while the video is playing, a question for you to think of. Okay, so why to use this duplicated structure instead of using just a simple double pendulum? Why do we want to do that? Yeah, we have the fast and precise movement, which is a good answer on the level of what we get. The question is why they are fast and why they are precise. What factors influence that we can get a higher fast? Yeah, less mass. Why do we have less mass? What you can notice that when you get the double pendulum, maybe someone has seen in the in our laboratory, okay, what you usually get is that you have a motor here, and you have a motor here, direct drive or whatever. And as you probably know, the motor has certain weight. When you look at the structure that we had in our case, we were driving actively, we were actively driving this joint and this joint. So we needed to have the motors at the base, and the motor didn't need to move. That's exactly what you see on the video to the right. Yes, we don't have any actuated part on this. Okay, at least not responsible for the rotation on these moving elements. So we don't need to add the mass there. So if we don't have the mass on the moving arm, we don't have the momentum of inertia is smaller. So we can either using the same force, we can have a higher acceleration, or using the same acceleration, we need to apply smaller momentum, smaller torque in the motor to get the same effect. So smaller mass, and because of that, either smaller torque or the higher acceleration, depending on in which direction we optimize. What about the precision? When we have the structure, okay, I will simplify it a bit. When we have a structure of, let's say, double pendulum, and we apply a force to it, what happens? This component of the force, let's mark it in red, marks also as needs to be compensated by the motor here, yes, because it's just the motor that influences the fork. The second component, this one, is cancelled by the stiffness of the construction, by the mechanical structure. So the part of force influences this motor. But if we have if we apply a mass, keep an object that is under gravity, and let's say we keep the manipulator in the position and the mass is still here, this part of force is the bending force that tries to bend our arm. As you probably know, the thin elements will bend more easily than the thicker ones. So you need to add enough thickness of the arm to prevent bending from the force. What happens when we attach from another direction a second arm? Then, okay, it will not be very precise analysis of the physics, just to give you the intuition. So when we have this blue force, let's say that we just look at the left part, we just we just split the force to two components parallel to the link that is cancelled by mechanical structure, and the left one red that is still not compensated. Now we look at the second arm, and for the second arm we just separate this part, and we just forget about this part, and say, okay, so we have this red force. This red force has these two components. This one is compensated by the mechanical structure, and we have that small part that is left. Okay, maybe it's much smaller than the than the original red and the original blue. Some of this, so out of the blue force, part is compensated by mechanical structure of left arm, part of the right arm, and only very small part really is applied to the arms as the bending force. So again, you don't need the dead thick arm. Of course, it is a simplification. So please remember that it's not how it is calculated, because what is wrong in these calculations is just that you cannot just start with the one part of the arm and then move it back to the second one. In fact, you would need to split the force from the beginning to the components for the left and right arm working together. So they need to be balanced from the beginning, but that's mainly the idea to show of what's going on. So bigger part of the force applied to the end effector is compensated by the mechanical structure itself. And because of it, this non-compensated part that needs to be non-compensated by these parallel forces, perpendicular part that needs to be compensated by the thickness of the arm to prevent bending, is much smaller. Therefore, again, the arms can be lighter. And because of that, we get a higher stiffness of the mechanism and higher precision of what is going on. Okay, and as we already had the term, so you know how to use it. Some of the applications, a simple application to the right. Of course, just to clarify, of course, when you look at the workspace, it is quite small relatively to the serial manipulators, and that's something that we will also have in all closed-loop manipulators. That the workspace will be much smaller. So, however, we say that these joints are independent, but the limits, the current state of each joint limits the movement of the second one. Yes. So if you move, let's say, the left arm to the maximum, to the maximally to the left, then you will limit the options for the second, the range of the second motor, because of these workspace conditions. Yes. So that will really happen, but and that will limit the workspace. But the gains in form of speed and the low mass causes that this type of the manipulator is used quite often, and we will see 2 examples in the end. Okay, so these examples are this parallel delta robot that is quite similar idea to what you see to the right, but not planar, but instead working in 3D space. So we have motors, 3 motors here, connect, and then the passive joints around here. So this is the passive joints, passive rotations that cause that we are moving this head here. As you can also see, how small are the arms that drive this robot. Yes, they don't need to carry the motors. All the motors are in the base. Therefore, they are quite light, and they can move really quickly. When you compare it to these industrial robots, the serial robots, as you could see in laboratory, the FANUC or ABB serial motor robot, you can see that the arms are much lighter in this case. And then why we get the higher speed. Okay, we always had some equations, so let's get into the equations of, okay, so we said, one more thing. return to the answers that you gave, we had 5 joints and 2 degrees of freedom. So the question is how to calculate them. And for that, we have so-called the mobility formula. And we will show the formulas here, but after that there will be an important disclaimer. So please also do not forget about the disclaimer later. So what we have, the mobility formula says how many degrees of mobility, degrees of freedom we have in our mechanism, let's say, and how to calculate it depending on the number of links that we have. That's the solution for the planar mechanism. So the mobility or the number of freedom is 3 times number of links minus 2 times number of joints and minus 3 times the number of grounded links. So we can calculate it quite simple when we the grounded links can be in most cases, in fact, the grounded links is treated as 1 because the common ground is treated as one grounded link. Okay, and when we look at the version for the a slightly extended version that is called the Kurzbach equation, it's quite similar, but because it just applies this G equals 1, so these 2 parts of the formula goes, 3 parts goes in here, but separates the number of joints of the 5th class and the 4th class, because 5th class joints that are used in Grubler formula are just the standard mechanism when we have only 1 rotation in a joint. The 4th class mechanisms are those which have 2 different motions in one joint. So that's why we subtract a bit less. Okay, we have this Kurzbach equation called like that. Sometimes when you go to literature, you will find a different name that will be called the Chebyshev-Grubler-Kurzbach criterion. But it's a different name for the same equation. The history was like that Grubler developed the first one just for this, just for the 5th class joints, and then the Kurzbach generalized it for the 4th class. At the same time, Chebyshev was working and got a similar formula, so that's why they are known under these different names. Okay, we can also get the so-called the general spatial formula, which is try to develop the similar formula for the 3D mechanism, and that's why we replace. Okay, let's say 3 from here. That was the 3 degree of freedom that we have in planar case, the x, y, and theta. We replace by x, y, theta. Sorry, x, y, z z theta phi psi. So we replace it with the base of 6 degrees of freedom, and we are just canceling it. So again, we have the number of links minus number of kinematic parts that we get, and we add the mobility of each joint. So if the joint has the mobility 1, we just add 1, and so on. Okay, there are two things to remember. Firstly, this formula, when we look at the mechanical part of the knowledge, causes is mostly used to distinguish between mechanisms and structures. Mechanism is something, just a simple difference is that the mechanism is something that has the degree of freedom B1 or more, so it can move, and the structure is something that has joints, but because of the mechanical constraints, it cannot move. So when you imagine, for example, this kind of the element, we have a ground, we have the rotational joint here, rotational joint, but we have an arm here, okay, a link here and a link here, and they are joined with the rotational joint as well in that place. And as you can see, and when you can calculate it from the formula, the degree of freedom that we get is 0. So in fact, it is not a mechanism, it is a structure, because it simply cannot move. Not so interesting for robotics. It's more interesting for the construction. Although the fact that they cannot move is somehow called in building some extending the let's say the stiffness of the mechanism with some additional stiff parallel part that can transmit part of the force from the main mechanism. Okay, so we distinguish mechanisms and structures. What we need to remember that, okay, the formula is not correct. Okay, it is like a necessary formula. So to get mobility, you need to have this this formula fulfilled, but it may happen that that for specific conditions, a structure will not, the formula will not give us a proper answer for the number of degree of freedom, especially when we have so-called redundant or parallel constraints. What are the parallel constraints? Is when we imagine such a construction. Let's say we have a block at the top, we have a ground, we have joints here, and we just connect these joints to the block. And as you can see, this block you can rotate. When you rotate these joints in here, it can freely rotate in some conditions, and in some conditions it cannot. When it will be able to freely move to the, let's say, in this swinging motion left and right, rotating the joints, and when it will not be possible. Just a second case that I'm going to plot. Same block, same joints. and let's make these connections. So I hope you can hear you can see here the difference. If the lengths of these links here are the same and they are placed symmetrically above, then we will keep this 1 degree of freedom motion of the top block. When the lengths are different, we will have 0 degree of freedom. In fact, the formula will give us 0 degree of freedom of this mechanism. But if in certain conditions, because of the certain length, the lengths and the symmetry will cause that we will have so-called redundant, or sorry, in this case it will be parallel, but parallel is like a kind of a redundant constraint type. In fact, the degree of freedom for this will be 1. So that's something that you need to remember, that okay, formula works in general case, but the special conditions related to the lengths may cause that the formula will not work correctly, and we will get a different results of the mobility. So it can be a hint in calculations, but not always exact formula. Why do we talk about it? We were saying that we have this parallel delta robots. We have another type of the typical, let's say, industrial, commercially available parallel robots, which is Stewart platform, that we have this supporting mechanism. We have either 2 degree of freedom rotations at the base, or 1 degree of freedom and 1 prismatic joints with translation here, and we just control the space of the top. So the movement, mostly rotation of this base. It is used in some very precise control of the orientation. For example, using the controlling a telescope that observes distant galaxies. The precision of this rotation that is given by the parallel mechanism and the forces that it can transmit, that is used in that application, that we need to very precisely move very heavy objects. Okay, so we already said about the properties: higher stiffness, increased precision, higher acceleration, force limits that we get. We get small workspace and additional joints constraints. And something we were not talking yet, we have a very complex kinematic equations, because we get this two-boundary constraint for the kinematic chain. So the kinematic here for the parallel mechanism is difficult. Much simpler is to solve the inverse kinematics, because it may be solved by, for example, in the case like here, when we know where this place is going to be, we don't solve it for 6 degrees of freedom. We just solve it like for each of the arm. We can solve it separately. So instead of that many joints as we already have, we just solve it for, like, let's say, like here, like 2 pendulum. So quite a simple case to solve. Okay, and that will be all. Maybe just one more remark. Okay, so who works on this and consider these different mechanisms, and why people think about, especially about these formulas and about mobility? It's the part of the robotics that you can find in mechanical departments. A part of these standard universal robots that one usually associates with robotics, people on the mechanical department, they work on the mechanisms that are able to make quite complex movements using as few actuators as we have. So that's a kind of the task that they are solving. Is like, okay, let's say that we want to have a robot for the special industrial applications that will get, let's say, this point, this point, this point, and let's say this point, because in these 4 points we have something to do on our production line. But we don't want to have a general 6 degree of freedom manipulator. We just want to have a manipulator with 1 degree of freedom. So we just want to control it with one motor. And they developed the mechanical people. They developed the mechanism, parallel mechanism that can really follow that. So follow the task by the proper shaping of the mechanism that we get. Okay, so it's as a summary, that's a view to a little bit distant field that's more related to the mechanics, but that's probably good, even if you are in electronics and you develop the electrical boards and the control system to know of what you control and what the mechanism can be and what are the options. And also what I always find important is, okay, usually when you go and work in the field, you need to communicate with people with from other fields, and you need to understand what they are talking about, and you don't really need to be able to solve their problems, but you need to be able to communicate and understand of what are the issues and what are the main characteristics of the things that you will commonly be working on. Okay, so that will be all for that. And as a summary, as you can see, the control question that will go for the exam, the main important points. What are the tree structures? What are closed chain structures? And what are the unique problems and the properties when we deal with parallel robots? Okay, so thank you for your attention. If you have any questions, please ask. We have like 3 minutes yet to answer them. Okay, I'm just recalling those who are planning to come beyond the project. Please mark in the doodle. I saw that some of you want to participate online, but if someone wants to be stationary, please let me know in the doodle as well. Okay, if there are no more questions, then thank you for your attention. And we'll finish for today. Bye.